All right, so let's look at chapter 3, calculus number 53. And so this is another particle moving along a line problem, and they give you the position function. And so over here on the side, I'm going to write down the units. So S is in meters, T is in seconds. And so the first question is find the instantaneous velocity at any time t. Since we have the position function, we know the velocity function is really just the derivative of the position. So the derivative of s, you can also write it as s prime t if you wanted. Now before you take the derivative, we haven't actually learned how we can take the derivative of something that looks like that. Where it's a function raised to a power, an entire function raised to a power rather than just a variable. So let me FOIL this part out first. So this S of t is really going to be t squared minus 4t plus 4, and then times t minus 4 next to it. That's this part. And then you could keep going if you wanted, but you could also just use the product rule on that. So that's what I'll do. I'm going to call this one u and this one v. So the product rule, uv prime plus vu prime. And now, let's see, u stays the same. So that's t squared minus 4t plus 4. V prime is going to be 1. And then plus v, which is t minus 4. And then u prime, 2t minus 4. So if we simplify a little bit, let's see, t squared minus 4t plus 4 plus 2t squared, that's that part, minus 4t minus 8t plus 16. And that's going to come out to be 3t squared. So there are the t squareds. Let's see, minus 16t plus 20. So that's my v of t. That's my instantaneous velocity at time t. Okay, so that's part A. Part B, find the acceleration at any time t. Well, acceleration we know is derivative of velocity. So that's v prime of t, or s double prime t. And here's v, and that's already in a nice form, so we can take the derivative of v and get 6t minus 16. So that, I'll write a of t over here, so I can just put that in its own box. Okay, part C says, when's the particle at rest? So when something's at rest, the way to interpret that is to think of it as the velocity is 0. So if we figure out when the velocity is 0, that's by, we just set the velocity equation that we found in part A to 0. And this is factorable. It's not super easily factorable, but it is. You could turn it into 3t and t, and then let's see, minus 2 here and minus 10 here. So that would work. But if you didn't know how to do it, since it equals 0, we can set up the quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a equals t. And so that would be positive 16 plus or minus square root 16 squared minus 4, 3, 20 all over 2 times 3. And if you work this out, you're going to end up with t equals 10/3 or 2. So these are our t values here. So that's when the particle's at rest because the velocity is 0. So I'll write it here, t equals 2 seconds or t equals 10/3 seconds. Actually, it's at rest with both of those, so I'm going to say and here. Okay. Then part D says, describe the motion of the particle. When does it change direction? Okay. So let's do the second part first. Change in direction. The way to interpret that is to think about the velocity. So if I'm moving forwards, the velocity is positive. If I'm moving backwards, the velocity is negative. So a change in direction occurs when the velocity changes sign. So when v of t changes sign. Well, we already know when v of t is 0. It's at 10/3 and at 2. So if I make a sign chart here, and I'm going to start it at 0 seconds and put 2 seconds here and 10 seconds. So this is my velocity line. If I plug in some sample numbers between 0 and 2, like if I plug in 1 into my velocity function up here, I'm going to get a positive number. If I plug in like 3, which would be a good test value here, you're going to get a negative number. And then if I plug in anything bigger than 10/3, like 100, I'm going to get a positive number again. So this says right here, velocity is positive, so it's moving forwards. Velocity is negative, so it's moving backwards. Velocity is positive, so it's moving forwards. So moving forwards, backwards, forwards. So that means that at t equals 2 seconds and t equals 10/3 seconds, the particle, is it a particle? What are we talking about here? Yeah, particle changes directions. And in fact, we can describe even more. We can say that the particle moves forwards from 0 to 2 seconds. It's moving backwards from 2 to 10/3 seconds. And it's moving forwards again from 10/3 seconds up to just whenever, infinity in this case, seconds. Okay, hope that helps.